This third part, we will talk about half-life of radioisotopes. So there are some calculations in this section. Okay, so let's talk first. What is a half-life? The half-life of an isotope is the time for the radiation level to decrease, right, to decay to about to 1/2 of the original value. Right. So for example, if I have here 20 milligrams of radioisotope iodine isotope 131, after one half-life has occurred, if I start with 20 milligram, I would now have 10 milligrams, right? So iodine, 10 milligrams of it have turned into xenon, for example, in this case, right? Iodine becoming xenon. So that's one half-life. Now, another half-life occurs from that point. We call the second half-life. When that occurs again, it splits it into half again. So now, based from 10, you will go down to half, which is to 5. So it's not like you multiply it across. It's not like you lose 10 milligrams here and then you lose another 10 milligrams there to make 0. That's not how decay it's going to work. So radioactive decay will work in terms of half-life, right? So half the amount, there is an amount of time called the half-life where half of it will disappear. So, and that time doesn't change. It's going to be constant. So let's say, for example, the half-life of this guy is, I don't know, 80 days, okay? I actually don't know. Let's say it took 80 days for this to occur. So after 80 days, you start from 20, you become 10. Another 80 day will happen until you have 10 milligrams. That's the second half-life. And then a third half-life occurs. Another 80 day is when you cut it in half again to become 5 and 2.5 and so on and so forth. So that's the definition of half-life. Oh, actually, that was iodine 131. I should have looked ahead to see the data there. One half-life of the sample decays every 8 days, not 80 days. So as you can see from the chart here, in terms of time, it's not a linear decay. It's kind of this exponential-like decay. The first 8 days, you lose 10 milligrams. The second 8 days, so day 16, you lose a quarter. And then the third 8 days, so in day 24, you lose another eighth, and so on and so forth, right? So you lose less as time goes by. But notice that time is constant. It's always going to be 8, 8, 8, 8 days. So every isotope has its different half-lives. You can call it a lifespan. Some things are very, very long-lived. Like, for example, carbon-14, the isotope, its half-life is 5,730 years. Actually, carbon-14 is the element, if some of you like forensics, is used to carbon date, right? To tell archaeologists how old this ancient script is. Is it 5,000 years old? Is it 10,000 years old? So on and so forth. Actually, there are isotopes that are even longer lived. For example, uranium, right? Its half-life is 4.5 times 10 to the 9th years. That's a long time. And then there are some things that are more common in medical occurrences. Like, for example, you might heard of iodine 131 for thyroid treatment. It has, again, a half-life of 8 days. Or technetium, it has a half-life of 6 hours. Right? These are things used in the medical fields. Okay, so I will walk you through 2 examples of how half-life calculations can be done and therefore can be asked in this class. Let's go inside where I have my tablet to do these problems. So let's read this first problem. It says the radioisotope strontium-90 has a half-life of 38.1 years. Okay, so pause. Remember that just means that after 38.1, after every 38.1 years, the amount of the amount of activity or the amount of material of that radioactive material is going to be decreased by half of the amount. Okay, so let's continue the question. If a sample contains 36 milligram, how many milligrams will remain after 152.4 years? Okay, so we have given that there's a certain starting amount, and after a certain amount of time, how much is left. So that tells us that we need to calculate how many half-lives has passed in these amount of years. So in this class, the amount of half-life will be very straightforward, as in it will be in terms of integers: 1 half-life, 2 half-lives, 3 half-lives, 4 half-lives. Of course, you can have non-integers like 3.4 or 3.5, etc., but we will not have that in this class. Okay, so let's calculate how much 152.4 years is in terms of half-lives if we know 38.1 years is 1 half-life. So so some of you can do that math in your head. You can just think of 152.4 divided by 38.1 is how many half-lives, right? So, but let's do that systematically using half-lives as a conversion factor, right? So using this as a conversion factor, we are going to convert 152.4 years into half-lives. We know that there are 38.1 years in 1 half-life of strontium-90, right? So if we do that calculation, we will see that how many half-lives have gone by. So we go to 152.4 divided by 38.1 will give us 4. That's our answer. So 4 half-lives. Right? Well, that wasn't the question though. The question was how many milligrams will remain. Okay, so that means we have to go back to the idea of what a half-life is. And remember that a half-life is half of the amount remains after that amount of years, right? After 1 half-life. So we have to do that half-life calculation 4 times over. So let's do that. So if we start at the original amount is 36 milligram, we say to ourselves, after the first half-life, I'm going to abbreviate it as HL now. After the first half-life, how many is left? Remember, by definition, half-life means it's just half the amount. So you take 36 divided by 2 is your half, right? 18 milligrams are left. Okay, again, we need to do that 4 times. So let's do it. Okay, the second half-life, divide that by 2, give you 9 milligrams. The third half-life, divide that by 2, give us 4.5 milligram. And lastly, the fourth half-life, divide that by 2, gives us 2.25 milligrams. Well, that's the answer. And we don't worry about sig figs at this point, okay? All right, so that's one type of problems you will see in calculations concerning half-life. Let's see what other types you can have. And to see that, we're gonna check out this checkpoint. It reads strontium-85. Remember, there are different isotopes. In this case, this is strontium-85, and it has its own half-life of 64 days. The question is, how long will it take for the radiation level to drop to a quarter of its original level? All right, so this question is a little bit different. It's not asking about for how much, but it's asking for how long. So in terms of time instead of mass, right? Or activity. But it's the same concept. We're thinking about half-lives. So it's asking for us to figure out how long to take to 1/4. So you have to ask yourself, how many half-lives does it take to be 1/4, to be a quarter? Can you do that in your head? How many half-lives is that? Well, if not, let's do it systematically, step by step. I start with a whole, right? 1 is a whole. Since a quarter is a percentage, I'm gonna start with 1 as a whole. After 1 half-life, how many is left of a whole? By definition, a half, right? So in fraction terms, that's 1/2. And then I do that again because I want to eventually go to 1/4. Can you see the answer already? After the second half-life, what do you get? 1/4. There you go. That's the answer. You need 2 half-lives to get to 1/4 of your original level. Yeah, we just do this one more time just for fun. This is not part of the problem. But what if I asked you, what is, after the third half-life, how much do you have left? What would you say? 1/8, right? Very good. So, okay, again, that was just for extra. That's not part of the problem. The problem deals with to 1/4 only. But again, that's not the answer because it's not asking you how many half-lives, it's asking for how long. But remember, our conversion factor is that we know for 1 half-life is the amount of time, in this case, 64 days. So we simply say that there are 2 half-lives, right? So we say 2 half-lives. And we know that for every 1 half-life, there are 64 days. So that simply means we just do 2 times 64 equals to 128 days. Simple as that. 128 days.